Hello everyone. Today we are going to finish off our unit on sequences and series, and we're going to discuss infinite geometric series. So an infinite geometric series is a geometric series that goes on forever and ever and ever and ever, right? So we're going to essentially add infinite terms of a geometric sequence. And we're going to do, before we actually really dig into what that means, we're going to do a little bit of an exploration. Okay. So first, what I'd like to do is let's look at what happens as n approaches infinity, right? The number of terms increases if we have the following conditions. So the first thing I'd like to look at is, what if the common ratio is greater than 1? So let's say we take a nice easy ratio of, I don't know, let's start with this example where we have 2, 10, 50, 250. So you can see what I'm multiplying here by is 5, right? 250 times 5 is 1250, 1250. Okay, so here our first term is 1, right? R is greater than 1. R equals 5, in fact. So T1 equals 1 and R equals 5. Okay, so if we want to look at Sn, right? Well, S1 is going to be 2. S2 is 2 plus 10, which is 12. S3 is 2 plus 10, which is 12 plus 50. So 50 plus 12 is 62. And then S4 is 2 plus 12 plus 50 plus 250. Well, up to S3, it's 662. So 62 plus 250, I'm doing this on a calculator, by the way, is 312. And S5 is... well, it's going to be 1250 plus 312, right? Because it's the first 4 terms plus the next term. So plus 312, let's see, 1562. Okay, so let's see what's happening. As the term number gets bigger, the sum also gets bigger. And it gets like considerably bigger quite quickly. Okay, so we can kind of make a generalization that as n approaches infinity, the sum is also going to approach infinity. Right? Because in fact, it's getting much larger than the sum number, right? When n is 1, the sum is 2. When n is 2, the sum is 12. When n is 5, the sum is already in the thousands. Okay, so whenever the common ratio, oh, I should have made this a 1 actually, is bigger than 1, this is what happens. Okay, let's see what happens if we have a common ratio that's less than 1. So let's say we have our less than, or negative 1, I should say, not less than 1, but less than negative 1. So I'm going to take this example. Let's say 3, negative 6, 12, negative 24, 48. Okay, so I'm just looking at the first 5 terms. So what's happening here is I'm multiplying each term by negative 2. Okay, so in this case, R equals negative 2. Okay, so for Sn, S1 equals 3. S2 equals 3 plus negative 6. 3 plus negative 6 is negative 3. S3 equals 3 plus negative 6, which is negative 3, plus 12, which is 9. S4 is 3 plus negative 6 plus 12, which we've established is 9, plus negative 24. So 9 plus negative 24 is negative 15. And then S5 is, the first 4 terms is negative 15, and then plus 48 is 33. Okay, so if we try and make a generalization here, well, we really can't, because what's happening is that the terms keep flip-flopping over zero, right? Half of them are positive, half of them are negative. So we can't really say what's happening to the sum as n approaches infinity. Okay, we can't make a generalization. As n approaches infinity, the sum, Sn, doesn't approach anything. It keeps flip-flopping over zero. Half of them are positive, half of them are negative. Okay, so now what I'd like to do is look at another example. And in this example, we're going to look at what happens if r is between -1 and 1. So let's say, for example, what if r was a half or a quarter or even 0.9 or 0.99 or negative a third? Anything that's between -1 and 1. Okay, another way of stating this, by the way, is, or we could say the absolute value of r is less than 1, right? Its distance from 0 is less than 1. That's another way of stating this same inequality. Okay, so let's look at an example. Okay, so I've got, let's say we take this sequence, 6, 1.5. Okay, so if this is a geometric sequence, what I'm doing is I'm multiplying this by a quarter. Okay, because 1.5 is a quarter of 6. So to get the next term, by the way, I have to do these on a calculator. So 1.5 times a quarter. The next term is 0.375. And then I multiply that by a quarter and I get 0.9375. I multiply that by a quarter, 0.09375. Missed the zero there. I'm going to multiply that by a quarter and I get 0.0234375. And maybe I'll do one more, times 0.25. Okay, so I'm getting 0.005859375. Okay, I'm going to stop. Okay, so if I do S1, that's 6. Okay, now what I'm going to do is I am going to pull out my calculator. And actually, I'm going to do this using a calculator on my iPad so that you guys can see what's going on to find the other sums. Okay, so S2 would be T1 plus T2. So that's 6 plus 1.5. So S2 is 7.5. And I'm actually just writing these on a piece of paper so I can remember what they are, because we're going to fill them in our notes in a second. Okay, but I want you guys to see on the calculator what's going on. To get S3, we have to add the third term because 7.5 is the first two terms added. So I'm going to add 0.375. And I get 7.875. S4, I have to add the fourth term. So I'm going to add 0.09375. And I get 7.96875. Okay, and now I'm going to add the fifth term, which is 0.0234375. And I get 7.9221875. Okay, and I'm just getting a pen because I know I'm not going to remember this. And I'm going to add the very last term that we figured out, which is 0.005859375. And that is, I had the other ones written down, but I'm kind of going rogue here, you guys. unprepared. Okay, so that is 7.998046875. Okay, so what I'm hoping that you'll notice is that these numbers keep getting really, really, really close to 8 the more terms we add, but they never actually approach 8. Okay, so that's what we're going to discuss. Okay, so let's just actually write these down though. S1 was 1, and I have them recorded. So S2 was 7.5. S3 was 7.875. S4 was 7.96875. S5 was 7.9921875. And S6 was 7.998046875. Okay, so these numbers keep getting closer and closer to 8, but they're never actually going to reach 8. And so what we say is that this is an infinite series that converges at 8. Okay, so in general, when the common ratio is between -1 and 1, whoops, there we go, that's better. The sum will approach a finite number. Okay, and we say that the sum converges. Okay, as opposed to in the first two examples, when the sum does not either approach anything or approaches infinity, we say that those sums are divergent. Okay, so this sum converges, or this sum is convergent, and the other two sums are divergent. Okay, now there is a formula for the infinite sum of a series, and that formula is this, and I'm going to write it down for you, and then I'm going to explain why it is the way that it is, because in fact, in order to understand it rigorously, we need a little bit more math than we have right now. So I think we have enough to have some understanding of where it comes from, but we actually need a little bit of calculus to be able to have the full understanding. Okay, so the formula for the infinite sum of a sequence, or of a series rather, is this. Okay, that is the infinite sum. It's also written this way because remember, we've spoken about this before. T1 is sometimes called A. Okay, now I want to talk about why. And the reason why is this. If we look at just any geometric series, okay, the general term of any geometric series is this. It's Sn equals Tn times 1 minus r to the n over 1 minus r. Okay, well, if r is between -1 and 1, then as n approaches infinity, okay, r to the n, whoops, I should say, I was thinking ahead. R to the n, this term over here, okay, is actually going to approach 0. And so the sum is going to be Tn times 1 minus 0, which just becomes that. Okay, now why does that happen? Well, let's think about it. If I have, let's say my common ratio is a half, right? A half is less than 1. If I raise a half to a very, very large exponent, let's say I raise it to the power 100. That means I'm taking a half and multiplying it by itself 100 times. I'm having something 100 times. Think about taking a pizza and cutting it in half and then having that half 100 times. You are not going to be left with any pizza. You're going to have nothing left. So if you take something that's less than 1 and multiply it by itself an extraordinarily number of times, you're essentially going to be left with nothing. And so that is why this is true. Why, as n approaches infinity, r to the n approaches 0. And the formula becomes this. Okay, so I did want to give you some background as to why that is the way it is. Again, we can't prove it rigorously until you guys learn about a little bit of calculus. So I hope to see you guys next year in calculus so we can explore this a little bit more. Okay, now let's do a couple of practice questions. So determine whether each infinite geometric series converges or diverges. Calculate the sum if it exists. So the sum will only exist if the series converges. Okay, now what determines whether a series converges or diverges? It depends on the r value. If the common ratio is between -1 and 1, the sum will converge. If it is less than -1 or greater than 1, it will diverge. Okay, so when we are looking at each example, the first thing we need to do is look at what is r. And remember, you can find the r value by taking one term and dividing it by the term that comes before it. So let's say I go 1/5 divided by 1. Well, 1/5 divided by 1 is 1/5. 1/5, I should say, right? Anything divided by 1 is just itself. Okay, so r equals 1/5. That means that this is going to converge because r is between -1 and 1. Okay, if we look at this guy and we say, what is r? Okay, well, r is one term divided by the term before it, so I could do 16/8 or 8/4, and that's 2. 2 is not between -1 and 1, so this series diverges, and we cannot find the sum. Okay, for this one that converges, the sum is T1 over 1 minus r. And T1 in this case is 1. So that's 1 over 1 minus 1/5. And that is 1 over 1 minus 1/5. That's like 5/5 minus 4/5 is 1/4. And remember that 1 is the same as 1/1. So you can write this as 1/1 times the reciprocal of 4/5, which is 5/4. And that is 5/4, or if you want to write it as a decimal because this one terminates, 1.25. Okay, so that is it for today, and that concludes this unit. I will see you guys